All right. Yeah. Proposition 9 is nice and simple and straightforward. To bisect a given rectilineal angle. Rectilineal, by the way, just means that the lines that are sort of creating the angle are both straight lines. Um, let's see, there is something interesting historical about that because who was it? Maybe it was Aristotle or somebody at some point kind of came along and started saying, hey, does it have to be the case that angles are always created by two straight lines? Like, for instance, if you think about like a circle and a line that's tangent to a point on the circle, you might be able to. There was for some time some discussion, as I recall. I might be just making this up. I'm just kind of going off of what I remember. But there was some discussion about whether or not the angle that is formed between the tangent line and the circle could be sort of rigorously discussed. Anyways, I better not say anything more about that because I've probably already said some things that are wrong, and somebody at some point, probably 3 years from now, is going to be like, you said this and it's not true, and then I'm going to have to make the video again. Right. So, just bisecting an angle, which I think that this is kind of an interesting one because it's maybe the first time that something comes up in this, in my opinion, in the elements where somebody who's not even a math person might go, yeah, how do you do that? Just given like what we have. So let's see here. Let's jump into it. So our angle is BAC right here. So we want to bisect this angle A. How do we do that? Step one, take any point. We'll call it D on AB. Any point that you like. Here it is. I'll call that D. Um, and then next, cut off AE on AC such that AE equals AD. And again, we saw this previously where this was sort of justified. This step was justified using Proposition 3, which was the one saying that if you have two unequal straight lines, you can cut off from the longer or from the greater line segment equal to the lesser. And so that's kind of what allows us, what justifies us to do this. But there must be some reason. I don't see why it couldn't just be, at least with these cases. It's just a circle. It's the circle of, with center A, radius AD, and then you find where that intersects. I guess maybe that's one reason that Proposition 3 is a little bit better here, like citing Proposition 3, because maybe, and I don't think that the Greeks would have thought this, but at least for our sort of reasoning today, we might say, well, how do we know that a circle, that circle that I created with center A and radius AD, how do I know that it actually intersects this line? So maybe that's a reason that Proposition 3 here is a little bit more solid. But for me, again, you just have to, at least as far as the construction goes, it's just a circle of radius AD and where it intersects here. So here is E. And then we will join DE. And if we wanted to justify that, again, which proposition was it? Do you remember? It's Prop 1. Or sorry, not Prop 1, postulate. Postulate 1 says we can join D and E. We don't even need a proposition for that. That's just a postulate. There we go. So there's DE. All right, then construct equilateral triangle DEF. And this one is Proposition 1. Right? It's Proposition 1. It's not even cited in my book. So apparently Euclid got to the point here where he was just like, it better be obvious. You better just know what I'm talking about. All right. There we are. So here's the point F of our equilateral triangle. And can you guess what the next step is? There's F. Guess what the next step is? Boy, oh boy, yep, you guessed it right. Join AF. Let's do that. So DEF, yep, and then join AF. And then we're done, at least as far as the claim goes. Claim angle, let's see, which one do they use? We could use either one, DAF. Says that the angle, oh right, he says, I say that the angle BAC has been bisected by the straight line AF. So, yeah, maybe angle BAC is bisected by AF. And of course we need to prove that. Well, what would the proof look like? This is the same as saying we really just need to show that angle BAF equals angle CAF. That's what we would need to prove in order to prove that AF has bisected this angle, because that would mean that it exactly cut the angle in half if BAF equals angle CAF. All right, how do we prove it? Well, what do we have? We know that AD equals AE. This is just by construction. And they share the side AF. What comes after that? The two sides DAAF are equal to the two sides EAAF. So DA and AF, right, are equal to EAAF. And let's see, so we're trying to use proposition 8 side, side, side. I'm just trying to like figure out the best way to kind of put all of this together so it looks nice and clean and it's not kind of like strangely worded. And the base DF is equal to the base EF. Let's see. So let's write that. DF equals EF. And this is again by construction. So we know that AD is equal to AE. We know that DF is equal to EF. How might I say? I'll just say it's kind of arbitrary, but I'll say they have in common the line AF. So, by I8, proposition 8, which was side, 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 and it's stated in a specific way. Proposition 8 was stated in a specific way, but basically because of these pieces, AD equals AE, DF equals EF, and then they've got the common side AF. So we're kind of looking at like this triangle right here, and then this triangle right here, sort of like if you look, this looks like a kite. Oops, sorry, it was a little bit high there. This looks like a kite to me, so we're looking at like the two triangles that form this kite. And we're saying that those are the same triangle by side, side, side. But moreover, more to the point, by proposition 8, we get that angle DAF equals angle EAF, which is the same thing, right? Because D lays on the same line as B, so BAF and DAF are the same thing. Same with E and C. EAF and CAF are the same angle. And that's it. Boom. We've proved it. Let's see, here's actually the first time, at least in my translation, that they use the acronym QEF, which basically means I constructed what I was supposed to construct. I don't know why QEF was not used on some of the earlier propositions. Like, proposition 1, proposition, right? Because proposition 1 was constructing an equilateral triangle. Proposition 1 through 3, really, they're all construction proofs, but for whatever reason, QEF is not used in there. Like, I know that the difference between QEF and QED, QEF is like, here, I've constructed what I was supposed to construct. QED is more, I've proven what I was supposed to have proved. But I don't know exactly why QEF is used sometimes, QED is used sometimes, and then sometimes too, let's see, oftentimes, at least in my translation, alongside QED, they also have therefore, etc., which is cool. If I was to go back to graduate school, sometimes I still think about it to go get like my doctorate. Probably not. But if I ever do go back, you can bet that when I am ending my proofs, I'm going to end them with therefore, etc. instead of QED. So, therefore, etc.